Earthquakes are caused by shifting tectonic plates that over time move, and at a certain point, when too much pressure builds up, they can snag or suddenly slip, causing the stored energy to be released as seismic energy. A civil engineer should apply their knowledge to reduce the damage caused by seismic risks on the built environment and therefore people. The average lifespan of a building is around 50 years. However, the return period of an earthquake is roughly 100 to 200 years. This means that making earthquake-proof buildings would be incredibly impractical, as they would be very expensive and their lifespan would more often than not be limited before they were subject to an earthquake. Therefore, as civil engineers, we must design earthquake-resistant buildings instead. This means designing buildings that ensure safety by preventing total collapse. To do this, we employ a few different methods to make buildings earthquake-resistant. Firstly, we focus heavily on ductility and flexibility, so that structures can dissipate the seismic energy without sudden failures or brittle fractures. Buildings that are too brittle tend to fail under seismic forces, as they have no way to dissipate energy, like the buildings shown here. We also try to avoid dead floors or irregularities in shape or mass. This creates a structure which is evenly strong and prevents failure in certain regions, as shown in this photo. If this is not done, certain regions can be weaker or be put under greater strain, causing them to fail, as shown. These are the main types of irregularities in buildings that should be avoided. Another method to make buildings earthquake resistant include bracing and cross bracing. This channels the horizontal force from the earthquake into axial forces and dissipates across the entire building, preventing higher levels of stress at one specific point and reducing the risk of failure. Using all of these principles, we designed a 3-story building that would have an egg placed on top that would have to withstand an earthquake simulation. Our building did not collapse, as we created an incredibly strong bottom floor, as can be seen here, with lots of bracing and reinforced beams made of spaghetti and straws. This prevented failure at the bottom floor, where all the seismic force was applied, and caused forces to be spread out over the entire building. We then created the upper floor to be more flexible to allow for movement and therefore the dissipation of the seismic forces. Overall, the building managed to survive the simulation test due to using most of these earthquake-resistant building practices, proving their functionality. These building practices are applied all over the world, especially in countries that are more susceptible to earthquakes. In 2010, Chile underwent an earthquake of magnitude 8.8, and only around 500 deaths were recorded, which is very low. The reason for this was due to Chile's strict code on earthquake-resistant buildings. This proved that strict codes did work in earthquake-prone areas. However, this earthquake also highlighted key points in the failure of some high-rise buildings, such as the Alto Rio building. Although built to the correct standards, it was constructed with particularly low-quality rebar steel, highlighting that, alongside building codes, buildings also have to be constructed to a higher level of quality. When designing earthquake-resistant buildings, we must also take into account possible geotechnical failures. Liquefaction is one such failure. This is when less compact soil, due to vibration from seismic forces, takes on properties similar to a liquid. As the granular soil loses its strength, this causes the foundation of the building to sink or tilt. To prevent this, techniques like compaction can be used to pre-compact and compress the soil before exposure to the earthquake. Another big geotechnical failure that can happen is landslides, where shaking can cause the shear force of earth to be greater than the frictional forces, causing loose earth to slide down. To prevent this, the soil can be compacted, which results in fewer landslides due to high internal friction.